Hello students, I am Dr. Sangeeta Sharma, your science teacher. Today we will be continuing with chapter 13 of your science book, that is magnetic effects of electric current. And in today's video, that is part 2, we will be studying about magnetic field due to a current carrying conductor. Students, in our previous video we studied that Oersted for the first time observed that a straight current carrying wire produces magnetic field around it. So today students, we will learn about this magnetic field produced around a straight current carrying conductor. So students, the magnetic field due to a current carrying conductor. An electric current through a metallic conductor produces a magnetic field around it. Now here we are taking a setup where we are taking a copper wire which is shown by this green line, and here we have indicated the directions. So if I put a battery and a key in the circuit and close the key, then the current will start to flow from the positive terminal towards the negative terminal. That is, the direction of current in this copper wire will be from north to south direction. Then we will observe that what happens to the needle of the compass which is placed just below the wire, that is the copper wire. So students, let's understand this experiment. So if we take a long straight copper wire, battery and a plug key and connect all of them in series such that the straight wire is parallel to and over a compass needle. Then on putting the plug in the key in the circuit, a current starts to flow in the circuit and the needle gets deflected. Now we will see the direction of deflection of this needle. So students, what we see is that if the current flows from north to south, here we have plugged in the key, you can see that in this circuit we have plugged in the key, so the current starts flowing in this direction. That is, the current is moving from north to south direction. From north to south direction. Then it is observed that the compass needle gets deflected in this way. Here you can see initially the compass needle was like this since it was pointing towards the north. Now the compass needle gets deflected. It gets deflected towards the east direction. So here you can see students that the compass needle has deflected towards the east direction. So if the current flows from north to south, the pole of the compass needle would move towards the east. The north pole of the compass needle would move towards the east. So here you can see, now if we reverse the direction of the battery, then what we observe? That the direction of current reverses. So does the direction of compass needle also gets reversed? Yes. So if we replace the cell connections in the circuit, the direction of current through the copper wire changes. That is, now the current will flow from south to north. If we change the directions of the battery, that is, we change the connections of the battery, then what we see is that the direction of current also gets changed. Now the current will flow from the south pole to the north pole. Then the direction of deflection of the needle changes. Now the needle moves in opposite direction, that is towards the west. Here in the diagram we see that if the connections have been reversed, here we have the negative terminal now and here we have the positive terminal. So the direction of current will be like this now. That is, the direction of current is now from the south pole towards the north pole. So the compass needle which was initially pointing towards the north and which got deflected towards the east when the current was flowing in clockwise direction has now get reversed. That is, the compass needle is now deflected towards the west. So here you can see this students, towards the west the compass needle has deflected towards the west when the current is reversed in the circuit. It means that the direction of magnetic field produced by the electric current is also reversed. Students, we know that the compass needle gives us an idea about the direction of the magnetic field produced by any source. Now here the compass needle's north pole gives us the direction of the magnetic field lines. So here students, what we see is that on reversing the direction of current, the direction of deflection of the compass needle also changes, indicating that the magnetic field produced by the electric current is also reversed. So students, the magnetic field due to a current through a straight conductor. Now we want to understand the magnetic field produced by a straight wire carrying current, and we have observed that the direction of magnetic field changes if the direction of current changes or gets reversed in the straight wire carrying current. Then now let's see that how does this magnetic field appear if we perform such type of an experiment. So here what we have taken is that we have taken a cardboard held stiff and we have sprinkled certain iron fillings over it, and then this copper wire is made to pass through a hole which is made at the center of this cardboard, and the copper wire is allowed to pass through it. Here you can see students, this green wire is the copper wire. Now this copper wire is connected to a battery through a ammeter, a rheostat and a key. Now what is observed is that students, when the key is closed, the current starts flowing in the circuit. So now the current in the straight wire starts flowing, and we can see the direction of current here students. Now what is observed that if the cardboard is tapped a bit, then what is observed is that the iron fillings arrange themselves in concentric circles, and if a compass needle is placed near the copper wire, then it is observed that it gives deflection, indicating the direction of magnetic field, that is the direction of magnetic field lines. So here students, if we connect a copper wire as shown in figure in series with a battery, a ammeter, a variable resistance and key, and sprinkle some iron fillings uniformly on the cardboard, then on closing the key, a current flows through the wire. On observing the pattern of iron fillings, we find that the iron fillings align themselves, showing a pattern of concentric circles around the copper wire. So what we see is that the iron fillings arrange themselves in concentric circles. Now students, what does this word concentric circle means? That all the circles having a common center or having a same center. So if this is the center, then all the circles which are drawn with different radii with the same center will be known as concentric circles. So what we observe is that if we have a straight wire carrying current and the current is flowing in the straight wire, then if the iron fillings are sprinkled around the wire, then these iron fillings arrange themselves in concentric circles, indicating that the magnetic field lines are as concentric circles around the straight current carrying wire. So students, these concentric circles represent the magnetic field lines. Now here students, you can see the green colored wire, which is the copper wire which we have taken in our experiment, and here you can see students that the iron fillings have arranged themselves in concentric circles. You can see this circle students. Here a pattern is shown which is of concentric circles, and the copper wire is passing through the center of these concentric circles. Then the direction of the north pole of the compass needle gives the direction of the field lines produced by the electric current through the straight wire. And if we place a compass needle, then the direction of the north pole gives us the direction of the magnetic field lines around this straight wire carrying current. The direction of magnetic field lines get reversed if the direction of current through the straight copper wire is reversed. If the current is increased, the deflection also increases. students, if the current is increased through the wire, then what is observed is that the deflection in the compass needle also increases, indicating stronger magnetic field developed. It indicates that the magnitude of the magnetic field produced at a given point increases as the current through the wire increases. So students, if the compass is moved away from the copper wire, but the current through the wire remains the same, the deflection in the needle decreases. अगर बच्चों कंपास नीडल को वायर से दूर लेकर जाया जाए तो कंपास नीडल का जो डिफ्लेक्शन है वो डिक्रीज हो जाता है. इसका मतलब क्या है? इसका मतलब ये है कि जैसे जैसे हम वायर से दूर होते चले जाएंगे उसका मैग्नेटिक फील्ड जो है वो डिक्रीज होता चला जाएगा. Thus, the magnetic field produced by a given current in the conductor decreases as the distance from it increases. So students, the concentric circles representing the magnetic field around a current carrying straight wire become larger and larger as we move away from it. So what we observed, students, that a straight wire carrying current produces magnetic field around it in the form of concentric circles with the wire at its center, with the wire placed at its center. So the properties of magnetic lines of force around a straight conductor. So we will now understand the properties which we have learnt by this experiment. So the first property is, students, the magnetic field lines around a straight wire carrying current are concentric circles whose center lie on the wire. The plane of the magnetic lines is perpendicular to the conductor, and the plane of these concentric circles is perpendicular to the wire carrying current. Moreover, students, the magnitude of magnetic field produced is directly proportional to the current passing through the wire and inversely proportional to the distance of observation point R from the wire. That is, mathematically we can write that B is directly proportional to I and inversely proportional to R. So if we increase the strength of the current, then the magnetic field hence produced will also become stronger. That is, the strength of magnetic field will also increase. And if we increase the distance from the current carrying wire, then the magnetic field will reduce. So students, right hand thumb rule gives us the direction of magnetic field. That is, this is a rule which gives us an idea about calculating the direction of magnetic field produced by a current carrying wire. So students, this right hand thumb rule states that if we hold the current carrying wire in our right hand with the thumb indicating the direction of current, students, we just imagine holding the current carrying wire in our right hand with the thumb in direction of current. Here the thumb is pointing in the direction of current. Here we have supposed that the direction of current is like this. Then if the thumb is pointing towards the direction of current, then the curl of the fingers gives us the direction of magnetic field. Here you can see that the curl of the fingers are like this. So a current carrying wire having current in the upward direction will have magnetic field in this direction. So this we have shown here. So if the direction of current is like this, then we have anti-clockwise magnetic field. This is the direction of magnetic field. Now if I hold the conductor like this and the direction of current is like this, then what I see is that the curl of the fingers will give me the direction of magnetic field. So if the direction of current is downwards, then what I see is that the direction of magnetic field is clockwise. So what I see is that the direction of current, if it is downwards, then the direction of magnetic field is clockwise. So this is the right hand thumb rule, students, which gives us an idea about the direction of magnetic field. So students, according to this rule, if we imagine the linear wire conductor to be held in the grip of the right hand so that the thumb points in the direction of current. Then the curvature of the fingers around the conductor will represent the direction of magnetic field lines, and this we have understood with the help of the diagram also. Now students, there is one more rule which is named as Maxwell's corkscrew rule, which also gives us an idea about the direction of magnetic field. Here students, we take a Maxwell's corkscrew, and if the direction of the motion of this corkscrew gives the direction of current, then the direction of rotation of the corkscrew will give us the direction of magnetic field. So according to this rule, if we imagine a right hand screw placed along the current carrying straight wire conductor, rotated such that the screw moves in the direction of flow of current, then the direction of rotation of the screw gives the direction of magnetic lines of force. This we will again understand with the help of a diagram. Now here students, we have a Maxwell corkscrew, and if the corkscrew is rotated, then the direction of rotation gives the direction of magnetic field, and the direction of the motion of this corkscrew gives us the direction of current. So if on rotation the corkscrew is moving downwards, then the direction of current is downwards, because the direction of motion of the corkscrew gives us the direction of the current. So if the direction of current is downwards, then we will rotate the corkscrew so as it moves downwards. Then the direction of rotation will give us the direction of magnetic field. So what we see is that when the current is moving downwards, the direction of rotation is clockwise, and if we rotate the screw anti-clockwise, then what we see is that the screw moves upwards. So that is the direction of current. If it is upwards, then the screw has to be moved in anti-clockwise direction, and if the screw is moved in clockwise direction, then the direction of current is downwards. So this was another way to find out the direction of magnetic field produced by a straight wire carrying current. So students, now we have understood what does a magnetic field look like for a straight wire carrying current, and we have read about the rules which gives us an idea about the direction of magnetic field. So now let's solve the problems given at the end of this topic. So students, we will solve the in-text exercises. So question number 1. Why does a compass needle get deflected when brought near a bar magnet? So students, why does a compass needle get deflected when brought near a bar magnet? So we know that a compass needle is also a form of a bar magnet, and we know that if two bar magnets are brought close to each other, then they are going to deflect each other. So students, a compass needle is a small bar magnet. When it is brought near a bar magnet, its magnetic field lines interact with that of the bar magnet. Hence, a compass needle shows a deflection when brought near the bar magnet. Now let's see the next question, which is example 13.1. A current through a horizontal power line flows in east to west direction. What is the direction of magnetic field at a point directly below it and at a point directly above it? अब बच्चों यहाँ पर करंट जो है, एक हॉरिजॉन्टल पावर लाइन के अंदर करंट जो है वो ईस्ट टू वेस्ट डायरेक्शन के अंदर है. तो स्टूडेंट्स यहाँ पे डायरेक्शंस हमने शो करी है, ईस्ट, वेस्ट, नॉर्थ एंड साउथ. तो हमें क्या पता करना है कि मैग्नेटिक फील्ड की डायरेक्शन क्या होगी जो इस हॉरिजॉन्टल पावर लाइन के जस्ट नीचे है और जस्ट उसके ऊपर है. यानी कि यहां पर हमें मैग्नेटिक फील्ड लाइन की डायरेक्शन पता करनी है और हमें यहां पर मैग्नेटिक फील्ड की डायरेक्शन जो है वो पता करनी है. तो स्टूडेंट्स, अगर राइट हैंड थंब रूल से हम मैग्नेटिक फील्ड की डायरेक्शन निकालें तो राइट हैंड के अंदर हमें पकड़ना पड़ेगा उस पार लाइन को, ऐसा इमेजिन करना पड़ेगा कि हमने पार लाइन को जो है वो राइट हैंड के अंदर पकड़ा हुआ है और थंब जो है वो डायरेक्शन शो कर रहा है ईस्ट टू वेस्ट। तो यहां पे आप देख रहे हैं स्टूडेंट्स, राइट हैंड के अंदर इस पार लाइन को इमेजिन किया हुआ है पकड़ा हुआ, और थंब की डायरेक्शन जो कि करंट की डायरेक्शन को इंडिकेट करती है, उस थंब की डायरेक्शन को हमने ईस्ट टू वेस्ट देखा है। तो जो कर्ल ऑफ फिंगर्स है वो हमें डायरेक्शन ऑफ मैग्नेटिक फील्ड देती है। तो अगर हम इन कर्ल ऑफ फिंगर्स को इस एंड पे से देखेंगे स्टूडेंट्स, तो वो हमें क्या नजर आएगा, वो हमें क्लॉकवाइज नजर आएगा। और अगर इस एंड से देखेंगे स्टूडेंट्स, तो ये जो कर्ल ऑफ फिंगर्स है ये हमें एंटी क्लॉकवाइज नजर आएगी। तो यानी ईस्ट से देखने पर तो क्लॉकवाइज नजर आएगा और वेस्ट से देखने पे एंटी क्लॉकवाइज नजर आएगा। तो जो स्टूडेंट्स मैग्नेटिक फील्ड है ना, वो डायरेक्शन ऑफ मैग्नेटिक लाइंस ऑफ फोर्स जो है वो कर्ल ऑफ फिंगर से शो हो रहा है और थंब से हमें करंट की डायरेक्शन शो हो रही है। एक तरीका और है स्टूडेंट्स कि यहाँ पे इस पॉइंट पे अगर हम मैग्नेटिक फील्ड को देखें तो हमें पता है कि फिंगर्स जो हैं वो बाहर की ओर पॉइंट कर रही हैं, यानी कि यहाँ से मैग्नेटिक फील्ड लाइंस जो हैं वो बाहर की ओर आ रही हैं। तो हमें पता है कि किसी पॉइंट पे अगर मैग्नेटिक फील्ड लाइंस परपेंडिकुलर हो और पॉइंटिंग आउटवर्ड्स हो तो हम उसे इस तरीके से शो करते हैं। बाय द टिप ऑफ द एरो we show the direction of magnetic field which is perpendicular to the plane and pointing outwards. Now students, at this point what we see is that the fingers are pointing inwards. So at the point just above the power line, what we see is that the magnetic field is perpendicular to the plane and pointing inwards. So here we can draw a cross with a circle. So here what we see is students that we can represent the back of a arrow as representing the direction of magnetic field. So what we put is, we put a cross and encircle that cross. This indicates the direction of magnetic field which is perpendicular to the plane and pointing inwards as the back of the arrow. And if we see the back of the arrow, then it appears to be like a cross. So students, we can show it like this, or we can explain it by the east direction and the west direction, that if we observe it from the east direction it will be a clockwise direction, and if we observe it from the west direction it will be a anti-clockwise direction. So we will write the answer like this. The current is in the east-west direction. Applying the right hand thumb rule, we get that the magnetic field at any point below or above the wire turns clockwise in a plane perpendicular to the wire when viewed from the east end, and anti-clockwise when viewed from the west end. Right students, I have shown you both the ways to answer and you can write the answer as you wish. So students, let's see the next question. Draw magnetic field lines around a bar magnet. This we did in our previous video students, and we can draw the magnetic field lines around a bar magnet so as that the magnetic field lines emerge from the north pole and merge at the south pole. So here we have shown the magnetic field lines emerging out of the north pole and merging at the south pole. Emerging from the north pole, merging at the south pole. Similarly, इमर्जिंग फ्रॉम द नॉर्थ पोल, मर्जिंग एट द साउथ पोल. यहाँ पे बच्चों हम क्या देख रहे हैं कि मैग्नेटिक फील्ड लाइंस नॉर्थ पोल से निकल रही हैं और साउथ पोल में एंटर हो रही हैं. तो यहाँ पे हम क्या देख रहे हैं, नॉर्थ पोल से जो फील्ड लाइंस हैं वो बाहर की ओर निकल रही हैं और साउथ पोल के अंदर जो मैग्नेटिक फील्ड लाइंस हैं वो एंटर हो रही हैं. So students, this is how we can draw magnetic field lines around a bar magnet. Now question number 2. List the properties of magnetic field lines. Now here we have to write the properties of these magnetic field lines. So the properties of magnetic field lines are, magnetic field lines emerge from north pole and merge at the south pole. So we can draw the diagram. We can support our answer always with diagrams. So whenever the diagram is required students, you must draw the diagram also. Then second, inside the magnet, the direction of field lines is from its south pole to its north pole. So we know students that outside the bar magnet, we have the direction of magnetic field lines from north to south. Here you can see, students, that the magnetic field lines are moving from north to south, but inside the magnet, these magnetic field lines move from south to north. So what we see is that inside the magnet, the direction of magnetic field lines is from south to north, but outside the magnet, it is from north pole to south pole. Moreover, students, the third property we can write as, thus the magnetic field lines are closed curves. Since they are closed loops, so we can call them closed curves. Fourth point, the relative strength of the magnetic field is shown by the degree of closeness of the field lines. So what we see is that more close the magnetic lines are, more strong the magnetic field is there. So what we see is that at the poles, we see that there is more number of magnetic lines clustered near the south pole and near the north pole. This indicates stronger magnetic fields near the poles. Here you can see this in the figure, students, that we have dense magnetic field lines at the poles. So this indicates that we have stronger magnetic fields at the poles. Then, students, we have one more property, that two field lines never cross each other. So no two magnetic field lines can cross each other. Now let's see the next question, which is question number 3. Why don't two magnetic field lines intersect each other? Students, we know that, and we have just written the property of magnetic lines of force, that no two magnetic lines of force cross each other. Why don't they cross each other? If they did so, students, and as we know that the direction of the north pole of the compass needle placed on the magnetic line gives us the direction of magnetic field line. So what we see is that suppose we have two magnetic lines of force which are crossing each other, and as we know that at any point, if we want to find out the direction of the magnetic field, then we can place a compass needle over there. Then the direction of the north pole will give us the direction of magnetic field at that point. So if I place the magnetic compass needle over here at the point of intersection, then what I see is that the direction of the compass needle, can it be at two directions? Can it show two directions? No. So at the point of intersection, then we must have two directions, but two directions of magnetic field at a same point is not possible. So what we say is that no two magnetic lines of force intersect each other. So two magnetic field lines don't intersect each other. If they did, it would mean that at the point of intersection, the compass needle would point towards two directions, which is not possible. So students, today we have completed the topic magnetic field around a straight wire carrying current, and we have dealt with the problems given at the end of the topic. Now students, we are ready to move further. So till the next video, stay safe, stay healthy. Bye.